In this video, we're going to look at a few interesting examples of open circuit time constants in action. We've been wrestling with the common emitter for a while, so let's see how open circuit time constants handle it. I've drawn a common emitter on the left here to kick us off. Here's a dynamic small signal model of the common emitter. Note that I shorted CE and CC because they cause low frequency pole zero pairs, not high frequency poles. And note also that I converted the input into its Thevenin equivalent, into its Norton equivalent. We can find the open circuit time constant for C pi pretty easily. One side of C pi is grounded, and if we open up C mu, then C pi will only see R pi and Rs in parallel to ground. And again, because C mu is open, we don't have to consider anything that's going on over here. There's just ground on one side, two resistors attached to the other. That's great, but C mu is kind of a mess. Neither side of C mu is grounded, so finding the Thevenin resistance that it sees is a bit counterintuitive. Just looking at this circuit, I don't know how to analyze C mu immediately. So I've redrawn the circuit, replacing C mu with a test voltage source, so that we can find the Thevenin impedance seen by C mu. When I do this kind of redrawing, I have to be really a stickler for labeling each node. So I've labeled VC, VB, and ground in this drawing. And I have to do that because you contort circuits in pretty unusual ways when you're redrawing them for open circuit time constants, right? It's weird that ground is in the middle of this drawing. But we do that because neither side of C mu is attached to ground. So keeping close track of the labels helps me do this accurately. Now, fortunately, redrawing C mu has revealed a pretty familiar pattern to us. It looks like C mu sees a left-right small signal pattern attached to it. So that means OCT C mu is equal to C mu times R left, RO parallel RC, plus R right, R pi parallel RS, plus GM times R left times R right. The left-right pattern is actually named after the behavior of C mu. R right is the resistance from the right side of C mu to ground. R left is the resistance on the left side of C mu to ground. So that's an easy way to remember the open circuit time constant for C mu. But it's also handy to keep in mind because you can often apply similar reasoning to much more complicated amplifiers, where if you find the impedance to the ground from the feedback cap on the right and the impedance to ground from the feedback cap on the left, they're going to wind up making something that looks like a left-right pattern. And that's a quick way to build intuition for tricky amplifiers. This is the S term from our exact transfer function, which I've pulled from earlier videos. And you can see that it's C mu times RC parallel RO plus RS parallel R pi plus GM RS parallel pi times RO parallel RC plus GM times RS parallel pi times RL, which is RO parallel RC, plus C pi RS parallel R pi. And that this exactly matches OCT C mu. So again, we get an exact estimate of our first order pole location using open circuit time constants, which is a better performance than we had with our Miller approximation. That said, the Miller approximation is still pretty insightful. You might notice that our OCT C mu contains a GM times an RC in it, which means we have our voltage gain multiplied by this resistance in order to predict part of that open circuit time constant. And so we expect Millerized caps to have big open circuit time constants. So even though we're not using the Miller approximation here to predict our bandwidth, it still grants us intuition about which caps are likely to create large open circuit time constants. Okay, so we had a great performance predicting the bandwidth of common emitter on the last slide. However, open circuit time constants can still fail. We're going to take a look at the worst case for open circuit time constants in a two-pole system on this slide. And I've put a two-pole transfer function on the top of the slide to kick us off. Alright, so if we substitute in the frequency we predict with open circuit time constants into this two-pole transfer function, we get this expression. And moreover, we know that the sum of our tau I is equal to omega minus 3 dB open circuit time constants, this predicted bandwidth, by definition, right? We calculated it as the sum of tau I. We said this second term was negligibly small. And that's true if tau 2 times omega minus 3 dB OCTC is small. And our worst case for that is if tau 1 is equal to tau 2. Because for any other value of tau 2, the tau 2 is going to have to be smaller than tau 1. Now if we then look back at this first term, we know that 2 tau times omega minus 3 dB has to be equal to 1 by definition, so 2 tau is equal to omega minus 3 dB OCTC. And subbing that relationship into our expression, we get that this last term is equal to 1/4. So in the worst case, with co-located poles, this last term is 1/4. So the transfer function for our actual two-pole system at our predicted bandwidth is 1 over 1 plus j minus 1/4. But the transfer function for our OCTC system, like the first order approximation we're using, is just 1 over 1 plus j. So there's about a 25% error in our worst case, and specifically we are predicting that our transfer function will be 25% smaller than the actual transfer function. And this is actually a pretty graceful way for our approximation to fail. It's underselling us. We're going to get a little more gain than we expect at high frequencies, and it's still. And one of the main takeaways about open circuit time constants is they're still quite good for intuition. They tell us which capacitors are causing us to have a slow amplifier. And that kind of intuition is the sort of thing that computer simulations can't provide. It's one of the reasons that you, as a circuit designer, are valuable. You can identify which caps are the problem and design around them. So open circuit time constants are still a great tool, even in the worst case. The error is not that big, it's in the right direction, and it grants intuition. So, in summary, the coupling cap and the emitter bypass cap cause zero-pole pairs in common emitter amplifiers. CMU sees a left-right pattern, where our right is the resistance to ground on the right side of CMU, and our left is the resistance to ground on the left side of CMU, which means that CMU, the Millerized cap, has a big Millerized open circuit time constant. The maximum open circuit time constant error is when poles are co-located, and in a two-pole system that means we'll misestimate our magnitude by about 25%. But even when open circuit time constant has high error, it's still pretty useful. First, the error isn't that big. Second, it makes a conservative estimate. And third, it gives us insight into what caps are slowing down our amplifier.